Hello. Welcome back to another lesson in Algebra 2, Unit 4. This unit is all about matrices and their application. In this lesson, we're going to discuss something very important called the determinant of a matrix, and then from there, we'll use the determinant to find the inverse of a matrix. Two very important things, so let's get right to it. The determinant of a square matrix is an important value that can be calculated from the matrix elements. The determinant of a matrix A is usually denoted with either these two vertical bars here, or occasionally you'll see it written in almost like this computer or calculator way of saying det for determinant of A. The determinant of a 2 by 2 matrix is calculated as follows. You multiply A times D, and then you multiply C times B, and you subtract those two. All right, so let's practice. So remember, the determinant of a 2 by 2 matrix is you multiply in this diagonal from upper left to bottom right, and subtract what you get when you multiply from bottom left to upper right. And it makes kind of that cross. So let's find this determinant. Notice the two bars. It's not the brackets that you usually see with a matrix, so that tells us it's the determinant. So 2 times 6 is 12, minus 1 times 3 is 3, so the determinant is 9. Let's find the determinant of this one. 3 times 2 is 6, minus a negative 2 times 1 is a negative 2, so this becomes 6 plus 2 is 8. Okay, the determinant of this matrix, 5 times 2 is 10, and 10 minus 1 is 10 as well. This matrix has a determinant of 0. All right, I'd like you to pause the video now, please, and attempt to find the determinant of these matrices. I have that one, that one, that one. All right, let's check our work. 11 times 2 is 22. Minus negative 2 times 4 is a plus 8, making it 30. All right, 4 times 2 is 8. Minus 3 times 2 is 6. That makes that 2. All right, 4 times a negative 3 is a negative 12. Minus negative 6 times 2 is a negative 12. So it's plus a positive 12. So this one is 0 as well. All right, well, we've seen a couple matrices now that had a determinant of 0. A matrix with a determinant of 0 is called a singular matrix. Out of example 3.1 and practice 3.1, there were two matrices that were singular. Which were they? What did you notice about how the values are related? So let's go back and look at them. Here's this one. And there's that one. Take note of what you notice. Well, I noticed that 5 times 2 is 10, and 1 times 2 is 10. I also noticed that looking horizontally, 5 divided by 5 is 1, and 10 divided by 5 is 2. Looking here at this one, 4 divided by 2 is 2, negative 6 divided by 2 is negative 3. There's also a relationship in this direction as well, because you could see that if you multiply 4 by 2 and divide by negative 3, if you multiply this by 3 and divide by negative 2, you would get 12 divided by negative 2 is negative 6, times 3 divided by negative 2 would be 6 divided by negative 2 is negative 3. So there's also a relationship here. It's a 3 over 2 kind of relationship, negative 3 over 2. So what we notice is that they are in proportion. The determinant of a 3 by 3 or larger square matrix can be found through a process called expansion. by minors. The expansion of minors is a kind of a tedious process, and we call it recursive in that you build out from a simpler version. So you start with a 2 by 2, and then you build out to a 3 by 3, which then builds out to a 4 by 4. And it turns out that finding the determinant of a matrix as big as, like, say, 7 by 7 is extremely time consuming. Would take several sheets of paper and at least an hour or so of work. So we won't look beyond getting the determinant of a 3 by 3, and we'll say a 3 by 3 would be could be then expanded out to 4 by 4. So basically, here's the way it works. If you want to find the determinant of a 3 by 3 matrix, then you've got to find the determinant of 3 2 by 2s. If you want to find the determinant of a 4 by 4 matrix, you got to find the determinant of 4 3 by 3s, which each one requiring 3 2 by 2s. So you can imagine that it just expands outwards and ends up being a lot of math. So the formula is basically this. The expansion by minor says what you do is you start with the element that's in this row and column, okay? And you list it here. You're going to multiply it, but you're going to multiply it times the determinant of the 2 by 2 matrix that results when you cover up that column and row. So if I ignore that row and I ignore that column, I find the determinant of this. All right, then after doing that one positive, you have to take negative of the next one, and again cross out the row and columns, and what would be left is this 2 by 2 here. When you ignore that row that B is in and that column, and you get D, F, G, I. And then lastly, again, you switch back to positive and you cover up that row and column and you get this. And so that's where the formula comes from. But for the 3 by 3 matrices, there's kind of a neat trick that makes it easier. If you just take the first two columns and rewrite them out to the side, then it turns out the determinant is this times this times this plus this times this times this plus this times this times this. So it's that same upper left, bottom right kind of thing 3 times. But then you have to minus, now coming up, just like before we minus when we went from bottom left to upper right, you got to go minus this times this times this, minus this times this times this, minus this times this times this. So it kind of gets kind of candy striped, like almost like a peppermint, candy cane or something, but that's kind of how it works out. All right, so let's practice. I'm going to find the determinant is 3 by 3. We discussed how to do it with the expansion by minors, which can be, that same process can be used for 4 by 4s and higher. But for the 3 by 3, let's use our special little trick. We'll say 1, 3, 2, negative 2, 2, negative 1. So remember, you just rewrite the first two columns, and here we go. We're going to multiply there, there, and there. So 1 times 2 times negative 3 is a negative 6. Then we'll do negative 2 times 1 times 2. That is a negative 4. The negative 1 times 3 times negative 1 is 3. All right, next I'm going to do 2 times negative 1. That's 4. That's a negative 4, so I minus a negative 4. Remember, we minus on the way up. Then minus, let's see here, negative 1 times 1 times 1 is a negative 1. And then I have a negative 3 times 3 times 3, so I minus, let's see here, negative 9 times 2 is a positive 18. All right, so notice that I always write the minus. I don't try and do minus to negative because then I lose track of which one I've calculated, which one I haven't. So now, after I've done them all, then I'll go back and change my minus negatives to plus positives. So we got negative 10 plus 3 is negative 7, plus 4 is negative 3, plus 1 is negative 2, minus 18 is a negative 20. All right, let's take a look at the next one. All right, this one's for you, so give it a shot. Okay, let's see how we did. 2 times 2 times 1, that's 4. Plus 1 times 0 times 3, that's 0. 1 times 4 times 2, that's 8. So we're done with the plussing. Now we're going to be doing minusing. Minus 3 times 2 times 1, that's 6. Minus 2 times 0 times 2, that's 0. Minus 1 times 4 times negative 1, that's a negative 4. Okay, so plus a positive 4. 4 plus 0 plus 8 is 12, minus 6 is 6, plus 4 is 10. Okay, the inverse of a non-singular 2 by 2 square matrix called A is calculated as follows. A inverse is equal to 1 divided by the determinant times that matrix, like, twist, if you will. So what we do is we take the A and D and we flip them. We change their location. You change them around, and then you make the C and the B negative. In the previous lesson, we confirmed that two matrices were inverses under multiplication because when we multiplied them, we got the identity matrix, which is where you have the ones in diagonal. This formula allows us to get the inverse. Remember, the determinant is actually just a scalar, so this is just a scalar multiplication. Notice that since we have 1 over the determinant, if the determinant were 0, then the inverse would not exist because 1 divided by 0 is undefined. So singular matrices do not have an inverse, and only square matrices can have a determinant. So they need to be square, they need to not be singular, then we can find their multiplicative inverse. We're not looking at the inverse of a 3 by 3 right now. There is a formula for it. It's just, more of the same. But for now, let's just look at the inverse of a 2 by 2 matrix. So let's confirm first that these two matrices are indeed inverses. So I'm going to take A, B, C, D. And that's kind of the thing. Why does this formula work? Can we be certain that it does? D, negative B, negative C, and A. All right, well, it turns out that I can multiply by the scalar before or after I multiply. So I'll just wait and do it afterwards. Okay, so we need to find the determinant of A. I want you to notice, though, that the determinant of matrix A is actually going to be the same as the determinant of getting this twisted version. It's still going to be A times D minus C times B. This is A times D, and then the negatives cancel. So it's interesting that the determinants are the same. So the determinant of A is AD minus BC. So we've got that calculated. We can wait and multiply by 1 over it at the end. So for now, let's multiply these two matrices together. So this is A times D plus B times negative C. So AD minus BC. Remember, when you multiply matrices, you multiply the row with the column on the right. Rows from the left, columns on the right. So I take the elements in this row, A and B, and multiply them with D and C, and we pair them up. A to D, B to C. B to negative C. All right, let's do the next one. I've got A negative B, so that's going to be a negative AB. Then I've got BA, so that's going to be a plus AB. All right. I'm just putting them in alphabetical order, right? Okay, we got CD, that's CD. And then we got minus D times C is CD again. All right, lastly, I got C negative B, so it's a negative BC. Then I've got DA, so we got plus AD. All right. Well, let's see what we can do to simplify this. Well, that's 0 and that's 0. Okay, so what I've really got here is just AD minus BC, 0, 0. And I'm going to call that AD minus BC just to change the order using the commutative property of addition. Now, that's not quite the identity, but remember, we've yet to multiply by 1 over the determinant. I've got to multiply by 1 over AD minus BC, which means each one of these terms get divided by AD minus BC. So this divided by itself is a 1. 0 divided by that is 0. 0 divided by that is 0. And AD divided by BC is 1. So indeed, it is 1001 as long as that number right there is not undefined. So this formula must definitely work. All right, so what I want you to do is I want you to find the inverse of the following matrices. Pause the video, use our formula, and do it. All right, so here we go. First of all, we need to find the determinant. So the determinant is -8 minus a -9, which makes it plus a positive. So -8 plus 9 is 1. So to find the inverse, I flip-flop the positions on this major diagonal, as we call it. And these 3 and -3, they change signs. Okay, and I'm going to multiply that by 1 over the determinant, which is just multiplying by 1. So apparently -4, 3, -3, and 2 is this matrices inverse. Shall we check? Yeah, let's check, just for fun. So 2, -3, 3, -4. What happens if we multiply that times -4, 3, -3, 2? We better get the identity 1, 0, 0, 1. So that's a -8 plus 9, that's 1. See, I'm doing the first row, first column. Then I've got 6 minus 6, that's 0. -12 plus 12, that's 0. 9 minus 8, that's 1. Boom, it works. So definitely, that's our answer. This was just me checking. That's our answer. That's the inverse. All right, let's try the next one. If you haven't already, pause the video and do it. But otherwise, let's go right through it. Okay, so to find the inverse, I need the determinant, which is 5 times 2 minus 2 times 4. So the determinant is 2. Okay, so what we'll do is we'll flip-flop the positions here. And we negate the numbers here. And we're going to multiply that by 1 over the determinant. So my inverse ends up being 1, -2, -1, and 5 over 2. And there we have it. Okay, so when using inverse matrix to remove multiplication, you need to pay close attention to the side the multiplication is occurring on. For example, if the matrix is on the left, we need to multiply by the inverse on the left. If we don't do that consistently, we won't get the right answer because we're looking for what left multiplies to do that. You almost have to think of multiplication as being two ways, left multiply and right multiply. We need to make sure we're consistent. Okay, so what I've got here is I've got a little algebra problem for us to do. We're going to solve this equation for the unknown matrix X. We've got 2, 5, 1, 3 times some unknown matrix X. X is not a scalar. X is a matrix. In fact, a 2 by 2 matrix. And then we're going to add this second matrix to it to get the final one. Well, let's talk for just a second. How would I solve something like this? If I had something like 7x plus 4 is equal to 25. How would you solve a question like that? Would you divide by 7 first? Well, you could, but then you have to multiply here and here and here by 1/7. So instead, let's subtract 4 from each side first, right? Then once I've done that, I can multiply on both sides by the multiplicative inverse. We're used to saying divide by 7, but, well, in here, I'm multiplying on the right. We're multiplying on the left in each case. So 1/7 times 7 is 1x, and then 1/7 times 21 is 3. So we're going to do this exact same thing. We're just going to be doing it with a matrix, okay? So here we go. First, we'll subtract this. We know that when you subtract two matrices, that you subtract the corresponding positions. They have to have the same size. 1 minus 1 is 0. That makes 0. That'll be plus 3, so that'll be 0. And then that'll be 0. So that's going to be gone. So I need to subtract it on this side as well. And I want to make that clear. When I get the matrix 0, 0, 0, 0 from doing this, that's the identity matrix for addition. So adding it to this unknown quantity over here, I just know that no matter what that is, it's going to be the same thing because that's the identity. So we have 2, 5, 1, 3 times x is equal to, over here I've got 3, -1, minus a negative is going to be, let me just distribute that minus actually. negative 2 plus 3 is 1. That just makes it a little easier for me to keep track. Negative 2 minus 1 is a negative 3. Okay? All right, now what I'm going to do is I'm going to find the inverse of this matrix and multiply by it on the left and right. So let's find the inverse. So I'm going to do that over here. I call this my inverse work, okay? Okay, so the determinant of that is 6 minus 5, which is 1. So the inverse then is flip the position around the diagonal from left, upper left to bottom right, and change the sign on the ones on the bottom left to upper right. Then we need to divide by each one of these terms by 1 over the determinant, which is just 1, so it doesn't change it. So we'll say 3, negative 5, negative 1, 2, times 2, 5, 1, 3, is equal to 3, negative 5, negative 1, 2, times 3, negative 1, 1, negative 3. So notice how I'm multiplying on the left on each case. This was left multiplication, so I need to do left multiplication. All right? So 3 times 2 is 6. Going in this row with this column. Negative 5 times 1 is negative 5. So 6 minus 5, can we just say that that is a 1? Now this row in this column. 3 times 5 is 15. Minus 15 is 0. Negative 1 times 2 is a negative 2, but plus 2 is 0. Negative 1 times 5 is negative 5. Plus 6 is 1. So that's what these two multiply to. They multiply to 1, 0, 0, 1. On this other side, we get 3 times 3 is 9. Minus 5 is 4. This row with this column. 3, 3, negative 5, 1. Now this row with this column. 3, negative 1 is negative 3. Plus 15 is 12. Then I have this row with this column. Negative 3 plus 2 is a negative 1. Then I have negative 1 times negative 1 is 1. 2 times the negative 3 is a negative 6. So that's a negative 5. So what does this tell us? Well, we know from yesterday's lesson it doesn't matter what side the identity matrix is on. If you multiply 1, 0, 0, 1 times matrix X, you will get the same matrix. As long as X is a 2 by 2 matrix, this will give you X back. So this is just X. But then over here, we have 4, 12, negative 1, and negative 5. That's saying that that was what our X must be. Well, if you don't believe me, and you shouldn't, let's check. So we're gonna check our work, okay? So let's check. I'm gonna put that right over here. So we're gonna check, okay? I've got 2, 5, 1, 3 times 4, 12, negative 1, negative 5, and then I'm going to add to that 1, 2, negative 3, 1. All right, so I'm going to go through this somewhat quickly since we've gone through this a few times, but I do want you to get the idea. 2 times 4 is 8, minus 5 is 3. 2 times 12 is 24, minus 15 is 7. I think. No. 24 minus 25. Oops, that's a negative 1. That's a negative 1. Sorry about that. I was thinking that was a 5 and a 3. Okay, 1 times 4 is 4. 3 times negative 1 is negative 3, so that's a 1. 1 times 12 is 12. Minus 15 is a negative 3. So that's what that equals. Now we got to add to that 1, 2, negative 3, 1. Well, what does that equal? Well, that is equal to 4, 1, negative 2, negative 2, which is exactly what we said it should equal. Pretty cool, huh? All right, you try this next one. Notice that the matrix multiplication here is on the right. You'll need to cancel it with right multiplication. All right, let's go over your work. Okay, so I'm going to find the inverse of this matrix. So I'll get the determinant. That's 9 minus 8 is 1. Again, that's convenient. So the inverse, I just need to flip-flop the positions there, which actually doesn't change anything. And then here, these just change numbers. So it becomes a -1 and a change sign. So -1, -8. So this is x times 3, 8, 1, 3 times 3, -8, -1, 3. That's a right multiplication, so I need a right multiplication over here as well. 2, 1, 1, 3 times 3, -8, -1, 3. All right, 3 times 3 is 9. 8 times a -1 is 9 minus 8 is 1. Yeah, so this is a 1. You might be wondering, why am I able to do the matrix multiplication here before I do x? Remember, we did talk about the associativity of matrix multiplication. I can't change the order between these three, but I can change which ones I multiply first. So as long as I keep x on the left, then this one, I am allowed to multiply these two together like so. All right, so I get... let's see here. Nine minus 8 is 1. Okay, I got -24 minus 24. That makes that 0, right? Then I've got 3 minus 3 is 0. I've got -8 plus 9 is 1. All right, so let's see what we get over here on this side. Remember doing the top row with the first column. Oh, on the wrong thing. So we've got 6 minus 1 is 5. -16 plus 3 is a -13. 3, this is a 3, right? Okay. 3 minus 3 is 0. -8 plus 9 is a +1. So that's what we're saying the answer is. Let's check our work, please. Well, I want to point this out. Remember, x times the identity is the same thing. So that's just saying that x is equal to 5, -13, 0, and 1. So let's go through that together. We've got 5, -13, 0, and 1, and we're going to multiply that. That's my x. So we're multiplying it on the right by 3, 8, 1, and 3. And if we do that, we'll get 15 minus 13. Well, that's 2. Then I get 40 minus 39. Well, that's 1. Then 0 plus 1 is 1. And then 0 plus 3 is 3. So it must work. We got it. And that is the end of a lesson. You can close by writing out the formulas for the determinant of a 2x2 and for a 3x3 matrix, because that's a key thing you want to make sure you understand from today's lesson. But after that, I'll see you next time.